Today, we're going to talk about the unsung hero of modern AI. Seriously, it's not a flashy name you hear all the time, but it's the bedrock, the foundation that makes pretty much everything you know about artificial intelligence actually work. So let's get into it. This one sentence from a really important paper back in 2012, it just cuts right to the chase. What it's really saying is that for an AI to be smart, it all, and I mean all, comes down to how it sees the data. And for a very long time, we were the ones telling it how to see. So I want you to think back to the early 2010s. All of a sudden, AI started getting good, like really good. Speech recognition got way better, computers were suddenly able to spot objects in photos, and language systems just took this massive leap forward. Now, on the surface, these all looked like totally separate wins in different fields. But here's the thing, they weren't separate wins at all. Microsoft's speech system, it cut its error rate by a staggering 30%. The winner of the ImageNet competition, it absolutely shattered previous records. And language systems like Senna, they hit brand new heights. The key thing you got to understand is that they were all connected by the very same underlying secret.
Let's just zero in on that ImageNet result for a second. The best anyone could do for identifying objects and images had an error rate of over 26%. And then, bam, it drops all the way down to 15.3. This wasn't just a little bit better. This was a total game changer. It was a sign that something deep and fundamental had shifted.
So that leads to the big question, right? What was this secret sauce? What connected all these amazing advances? Well, to really get the new way of doing things, we first have to take a look at the old way. And that old way, well, it was defined by this massive, incredibly slow bottleneck that we call the feature engineering problem. So before this big revolution, if you wanted an AI to, say, recognize a cat in a picture, you couldn't just feed it the pixels from the image. No way. You, a human expert, had to step in first. You had to sit down and manually code what features matter. Things like edges, curves, pointy ears, whiskers. You were essentially pre-chewing the data for the algorithm. And this was a huge problem. I mean, it required armies of PhDs who were not only experts in machine learning, but also in whatever specific field you were working on, like speech or computer vision. It was incredibly slow, the results were brittle, and, as the source paper points out, it was basically just a crutch. We were using it to compensate for the weakness of the algorithms themselves. We were holding the machine's hand, and it was holding back the entire field. So, the breakthrough, it came when researchers totally flipped the script. Instead of us telling the machine what features to look for, they decided to let the machines learn for themselves. And this is representation learning. The core idea is actually pretty simple, but it is so profound. You give the machine the raw data, the pixels, the sound waves, the raw text, and you let it figure out what the important features are. You let it build its own understanding, its own representation of the world. So when you put them side by side, the difference is just night and day. We went from humans handcrafting every little feature to machines discovering them completely on their own. We moved from a process that was slow and fragile to one that is automated and incredibly powerful. Instead of making up for weak algorithms, we started building algorithms that could finally, truly learn. Okay, so letting the machine learn its own features is the secret. That's great. But what does a good learned representation actually look like? Why is it so much more powerful? Well, the magic is in something called distributed representations. Think of it like this. The old way might have had one specific feature for pointy ear. That's it. But in this new way, the AI learns ingredients like pointiness, furry texture, or a bright angle. And by combining just those few ingredients, it can describe not just a cat's ear, but thousands of different things. It's an exponentially more powerful and efficient way to understand the world. Let's make this real. Let's use a face as an example. The very first layer of the network starts with just raw pixels and learns to see super basic things like edges and corners. Then, the next layer up, it doesn't see pixels anymore. It sees the output of that first layer, and it learns to combine those edges into parts, like an eye or a nose. And then a third layer combines those parts into the abstract idea of a face. This layering, well, that's the deep in deep learning. So, the absolutely crucial point here is feature reuse. That primitive little edge detector that the first layer learned, it isn't just used to build an eye. It gets reused for the nose, for the mouth, the chin, the hairline, all of it. It is an unbelievably efficient way to build a complex understanding out of very simple parts. But the ultimate goal is even more ambitious than that. It's about disentangling the underlying factors of variation. Okay, what does that mean? For a face, it means learning separate concepts for a person's identity, their expression, the angle of their head, and the lighting in the room. When an AI can do that, it's not just recognizing a pattern anymore. It's starting to understand the independent causes behind what it sees. And that is a huge step toward real intelligence.
And this is where it all takes us beyond just getting better scores on a test. This really points back to the original, much grander quest of artificial intelligence.
This all leads to a really powerful result. When an AI learns these core underlying factors, things like shape or texture or color, it can then share them across totally different tasks. The knowledge of what an edge is can be used for recognizing both faces and cars. We call this transfer learning, and it means that knowledge you gain in one area can dramatically speed up learning in a completely new one.
You know, the authors of the paper put it perfectly. They said, for an AI to truly understand our world, it can't just memorize patterns. It has to learn to identify and separate out these fundamental building blocks, these hidden explanatory factors, from all the messy, raw data it gets from the world. So, at the end of the day, that is the big takeaway here. This huge shift to representation learning wasn't just another small improvement. It was a fundamental change in philosophy. It was a necessary step away from just building simple pattern matchers and a step towards building machines that can form their own abstract, robust, and flexible understanding of reality.
And that leaves us with a pretty fascinating question to think about. As we build these incredible systems that learn their own ways of seeing the world, totally independent of our human-made features and biases, what might their unique perspectives eventually teach us about the structure of our own world?